The second type of growth pattern we see in populations, which is more common, it's called logistic growth. So please write this as your next heading. In this type of growth, the rate of growth starts out as being exponential, but eventually levels out. It levels out because the births and immigration, so our pluses, equal the deaths and emigration. Obviously, not every population is going to reproduce so quickly that it reproduces faster than the organisms die. So eventually, they have to become equal. Again, most biological populations experience logistic growth. And I'll tell you a little bit more about that, what that looks like in a moment. Okay, in this type of environment, the population does have these limiting factors. Again, remember, these are the factors that slow down growth, and I'll talk about them in a little bit more detail later. When you graph it, it looks like an S curve. So I want to show you what that looks like. Again, it's not a perfect S, but that's what they call it. So again, if this is your graph, you've got time down here, you've got number of organisms here. It starts out exponential, so it starts increasing really, really quickly, but then all of a sudden the deaths and the emigration catch up to the births and the immigration, so it levels out. It's kind of like a stretched out S. Okay? That's what the logistic growth pattern looks like. Some other characteristics. The population only grows as large as its carrying capacity allows, and we'll talk about that in a little bit here too, what that carrying capacity word is. But basically the carrying capacity is where it levels out. So just add that in. So if we look at our little S curve again, right there where it plateaus, that is the carrying capacity. CC, I'll abbreviate. So that's all the higher the population can grow, right? Is as far as that carrying capacity goes. Okay, so let's talk a little bit more about this carrying capacity. Definition you need to get in your notes. The carrying capacity is the maximum number of individuals the resources of a location can support. So again, if we're looking at a graph and we put some numbers to it, let's do our little S curve here. And this was time down here, remember? And this is number of organisms. Let's say this value right here is 100. Okay, 100 is where it levels off. So 100 equals our carrying capacity. So the carrying capacity for this population is 100 organisms. Okay, there's not enough food, maybe there are too many predators, there are things that it starts to run out of, some of those limiting resources, that if it gets any higher than that, organisms start to die faster than they're born. So the carrying capacity is that top level of organisms that the environment can support. Okay, now on to these limiting factors that I've been talking about and saying I'd talk about more later. We have two types of limiting factors. Please put that as your heading. The first kind are called density-independent limiting factors. Density, as you know, is how tightly packed the molecules in something are. So when we talk about the density of a population, we're meaning how tightly packed are the organisms. So if this population is affected by something regardless of how many organisms there are, that means it's density independent. Okay, so these types of factors affect a population regardless of how big or small it is. If it's a small population, these factors are going to affect its growth. If it's a large population, these factors are going to affect its growth. Density dependent is the other hand on this, and these will affect denser or bigger populations. So the more density a population has, or the bigger it is, the more likely these things are to affect it. Okay, so to make this a little less abstract, give you some good idea of what I'm actually talking about here, I want you to write down some examples. So on our density independent side, remember these are things that will affect a population's growth no matter how big it is. are natural disasters, like earthquakes, tornadoes, floods. They will affect the growth of a small population as well as the growth of a big population. Environmental changes, such as climate change. And then finally, migration, organisms moving from one area to another. Again, it doesn't matter how big or small that population is, it will be affected either positively or negatively in its growth because of those factors. The opposite side of this, our density-dependent factors, are predation, disease, and resources. So the higher a population gets, the more likely it's going to be affected by predation. And that's because there's just more prey for the predators to catch. So it is density dependent because bigger populations are more affected than smaller populations. Disease is the same way. Okay, when organisms are higher in number, when they're tightly packed together, those diseases, those bacteria or viruses, are more likely to hop from one organism to another. And so larger populations are affected more by disease than smaller populations. We know this from humans. Right? Whenever we have an outbreak of the flu or some other virus, we're going to see it in the bigger cities first before we see it in smaller areas. So it's density dependent. Larger areas affected more. Finally, any of the resources you can think of, food, water, shelter, things that organisms need to survive, are going to be affected by larger populations more. So if you have a larger population, it's going to be harder to come by enough food, enough shelter, enough water. And so it's going to have a bigger impact on your population growth than a small population. Small populations don't run out of resources as easily, and so resources is definitely a density-dependent type of factor.